So first of all, let's take it back to basics. So what is the LC-MS workflow and what does it look like? So the first part we consider is what samples and what analytes we're going to use. So different applications, this could be any food samples or water samples or drug molecules, whatever your application is. The second part to consider is your sample preparation. So this plays a fundamental part of the LC-MS workflow. However, today, what we're going to focus on is the first step, which is separation. So the next few slides, I'm going to talk about the HPLC system and the column. So step one, separation, the HPLC system. So here on the left, we've got our SciX Xeon 2. And the first part, I'm going to talk about what is in the top compartment. So we have our mobile phase A, which is usually aqueous, and we've got our mobile phase B, which is organic. Then we have our degasser, which is there to remove any air in the lines. And in this case, we've got a binary pump system. And the purpose of these pumps is to deliver mobile phase at both steady and precise amounts. And our mixer ensures our mobile phase is mixed before continuing to the column. So this is what is in this compartment of the HPLC system. The next part of the HPLC system we're now going to go through. So then we get flow to our auto sampler. We have a syringe here, which is shown in D. The syringe is used to pick up accurate amounts of sample. Then we have our column oven, which is shown here, and the diagram is shown on the right. And this keeps our column at consistent temperature. And our sample loop, which is loaded with sample during injection. So this is just what the HPLC looks like. The next part to consider in our separation is choosing a column. So the components of the mixture are carried through a stationary phase by a flow of mobile phase, and the separation is based on the differences in migration rates among the sample components. So typically on a column, you'd have, say, some silica particles with a stationary phase bonded to it, sometimes a polymer that is specific. And the smaller the affinity a molecule has for a stationary phase, the shorter the time spent in a column. So it's really important to choose the correct column for your specific application. So this is what a typical chromatography gradient looks like. So first of all, our mobile phase serves two purposes. The first purpose being to displace compounds from the stationary phase, causing elution. The second being to transport other compounds through the column and the rest of the LC system. So typically we start with a high aqueous starting conditions. We then ramp up to more organic, and as we ramp up to a more organic, we get more hydrophobic compounds eluting as our organic part increases. And then typically we would keep this part at high organic to wash any remaining analytes off the column, and then back to aqueous for column equilibration. So this is just a typical gradient. Now, if we touch on the second part today, which is the mass spec. So first of all, what information does a mass spec tell us? So we can gain molecular weight information, technically the M/Z, which is our mass to charge ratio. We can also identify the detected masses at any given time. And we're also able to look at some fragmentation information. Also, though, how can we use this data? So one way in which we can use this data is for quantification, so for quant. Another way, molecular formula identification. The third way, reproducible fragmentation patterns that gives us clues about functional groups, and these can be specific to, say, two molecules with the same M/Z and help us identify which one's which. So this is the information the mass spec will tell us and how we can use this data. So two main ways we can ionize is ESI, which is electrospray ionization, and APCI. We typically mainly use ESI. That's really common because, as you can see, it encompasses a large molecular weight range and it deals with molecules of polar and very polar. You can also use APCI typically in nitrosamine applications, but today we're mainly going to focus on electrospray ionization. So electrospray ionization, how are ions created in mass spectrometry? So we get our flow from the LC, and the flow is then dispersed into a fine spray of droplets. We're then able to form charged droplets. We get some heat, so we get desolvation and evaporation. Then we get ionic repulsion, we're clustering, and then our ions enter the mass spec. It's important to note that we have these other parameters, so we've got our curtain plate and our curtain gas, and the purpose of our curtain gas is to basically push away anything that isn't our ion of interest. So this just reduces solvent molecules and anything we don't want entering the mass analyzer. So how do our ions travel? So this is an example of what the inside of our 7500 system looks like. So we've got the orifice, we've got Q1, Q2, and Q3. So Q1 is where we identify our parent ion or precursor ion. Q2, this is our collision cell, so this is where fragmentation will occur. And then Q3, this is where we would then measure our product ions. So what is MS/MS? So just as we spoke about before, we get two mass measurements. So in just typical MS, we would only measure Q1, so we'd only measure our precursor ion. Where here, we're measuring both our precursor ion in Q1, fragmentation in Q2, and then measuring our fragment ions by a second mass analyzer in Q3. So now let's look at some data acquisition and workflows. So now our ions are formed, we then decide on our goals and we pick a specific workflow that's good to use for our application. So first of all, let's talk about traditional quantification, which is MRM. So this is what MRM scans for quantification typically look like. So as I said before, we've got Q1, where we identify our parent ion. In this case, it's 215. Then we have Q2, where fragmentation occurs. And then we have Q3, where we're selecting our product ion, and in this case, it's 185. So let's now consider the importance of MS data in comparison to MS data. So here we've got our standard, and we've got this P here, and here we've got a matrix blank and a spike sample. So when we're just using MS data, we're observing interference in the matrix blank and in the spike sample, as you can see here. So this is just MS data. However, when we use MRM data, as you can see, we're reducing or eliminating the interference in the matrix blank, which means we're going to reduce and eliminate in our spike sample, which makes it much more easier to identify. So now I'm just going to talk about some scans that are unique to our QTRAP system. So our QTRAP system can perform both quantitative and qualitative scans on the same platform and within the same experiment. So the two scans I'm going to touch on today is MRM³ and an EPI scan. So MRM³, this is a workflow for highly selective quantification. So at the beginning, it works exactly like MRM. So we select our precursor ion again, which in this case is 215. We then get fragmentation occurring in Q2. And then we get isolation of our ion. And we get another fragmentation occurring here. So we get a second generation product ion, and then this is scanned out. So we get basically a pair of product ions that are specific to our precursor ion, which obviously makes this much more selective. So now let's look at the benefits of using this scan, say for instance, over MRM for some applications. So here on the left, you can see we've got interference in our matrix blank, which means we've got interference in this spike, where when we're using MRM³, we're reducing the interference in the matrix blank, which means that we then get a reduction in our spike too. Now let's move on to the next data acquisition and workflow, which is MRM/EPI. And this can be used for multi-target screening. So MRM/EPI, works similarly to MRM. However, we set an intensity threshold in the software. So first of all, again, we select our precursor ion, which in this case is 215. We then get fragmentation occurring in our Q2, but this time we use a spread of 3 collision energies. The software then controls the fill time and the ions then exit. And from this, we get a fragmentation pattern. So how can this help us? So we look at this example here, is this phenoxycarb? So we've got our matrix sample here, and we've got our phenoxycarb QC here. And as you can see, there's been a shift of retention time in the matrix sample, and we're unsure whether this is phenoxycarb or not, because based on retention time, we can't really tell, because this could have shifted for numerous reasons. However, when we use the EPI scan, we look at our matrix bank here, we see we've got a fragmentation pattern. And if we compare this fragmentation pattern to the fragmentation pattern we get for the 1ppb QC, you can see the fragmentation pattern is completely different. So then we can say with confidence that this isn't phenoxycarb. So just to summarise, traditional techniques including LC-UV, GCMS suffer from cross-reactivity and inadequate selectivity. LC-MS it has many advantages, including accuracy and precision, robustness, sensitivity. We can get more confidence when identifying a specific compound, and we're able to analyse large panels of compounds and easily add in new analytes to the methods. So despite an upfront investment, the per sample cost with LC-MS is lower. If you want to look at this in a lot more detail, you can click on our on-demand series. So the next part of this highlight series is going to cover method development. So it's going to give you some tips and tricks on what you need to think about when developing a method. So let's think about the 3 steps of method development. The first step would be compound optimization. The second would be looking at your chromatography, which we've just touched on before, and we'll touch on a little bit more in this section. And the third would be our source optimization. So first of all, let's look at compound optimization. So there are 3 major experiments when thinking about compound optimization. The first being our Q1 scan, because we need to identify our precursor ion or parent ion. The second being our product ion scan, because we want to be able to identify our fragments. And then the third are MRM scans, and this is really where we're optimizing our parameters. So this is just a diagram of a mass spec, and this is kind of an infusion setup. So we'd have a syringe with flow going to the mass spec. So compound optimization. So as I said, the first experiment is a Q1 scan where we identify our parent. So during this step, we'll scan a given mass range that encompasses our analyte of interest. So here our analyte of interest is Vesperine, and we've got 608 Daltons. So we've chose our start mass and stop mass to encompass this. So our start mass is 605 and our stop mass is 635. So typically the mass range should be large enough to include adducts, and in general for a rule would be say plus 25 Daltons in positive mode, just so we've got a range where we're actually going to identify this molecule. Okay, so the second experiment in our compound optimization, now we've identified our parent ion, is our product ion scan. And this is where we want to identify our fragments of interest and see how this fragments. So typically for this, we'd set our stop mass about +1 Dalton of the parent mass or precursor mass. So here we've got our precursor ion is 609. So we've got our stop mass at about 610, so +1 Dalton. And here from this, you can see we get our fragments, and we can look at, you might have in mind how it's going to fragment, and you can identify which fragment is which. The third thing to consider now is our MRM scans, where we optimize our parameters. So the first thing could be to look at is the clustering potential. So typically the ideal declustering potential will be at the apex of the peak as you're optimizing your compound, and DP corresponds to the voltage applied to the orifice to minimize these solvent clusters. So DP is applied before any fragmentation occurs, and a compound's DP is dependent on the parent and not the transition. So because it's dependent on this, the DP profiles for the same compound should be the same. Therefore, we can't actually use DP to eliminate fragments that are unrelated to the parent. The second parameter in our MRM scan for compound optimization we could look at is collision energy. So again, the ideal collision energy will be at the apex of this peak. And after ramping RCA, you'll want to choose this value. And in general, as a rule, the smaller fragments will need a higher CE than larger fragments. Then we have collision cell exit potential. So CXP transmits the ions into the Q3 quadrupole, so that's the purpose of this. And typically it is between 10 to 15 volts. And again, you'll find the ideal CXP at the apex of the peak when you're doing your compound optimization. So now let's look at step 2, which is our chromatography. We touched on this a little bit more before, and it's in more detail in our on-demand series, but let's look at how column length affects things. So column length is directly proportional to both pressure and elution time. So for a given particle size, column efficiency will be directly proportional to the length of the column. And it's good to bear this in mind when choosing a column for a specific application. The next thing to think about is particle size. So as our particle size decreases, our pressure is going to increase and our peak width is going to decrease. So when choosing our particle size, we need to consider our sample and sample prep. The next thing to consider in chromatography is the selection of a mobile phase. So typically a great starting point is 0.1% formic acid and water for our aqueous mobile phase, MPA, and acetonitrile or methanol for our mobile phase B, which is typically organic. And here we've just got a list of buffers that we could use and pHs, and obviously this is completely specific and application dependent. So typically you'll most likely lose sensitivity as you increase the pH, but increasing ionic strength may also cause loss of sensitivity too. So these are just things to consider, and as I say, it is application dependent. Again, this is a sample gradient where we start off a high aqueous, we then ramp to more organic, and our more hydrophobic components will then elute. We then keep it at high organic as we wash the column, and then reduce the organic content and increase the aqueous content, and then we go into column equilibration. Okay, so the next part of this is our scheduled MRM methods. So once we've got the chromatography that you're happy with, we can then schedule retention time. So scheduling our retention time will improve dwell time and points across the peak. So scheduled MRM monitors each transition at an expected retention time. And this means that we can monitor more transitions while remaining to have optimum dwell time. So this is just an example of how we can set up an MRM method in our software. So step 1, we run a mid or high level standard. We then create a method in analytics, which we go into in more detail in our on-demand series. And then we are then able to copy and paste the retention times into the method. Now let's look at source optimization, step 3. So to optimize the source in this part of the presentation, we'll be looking at on-column source parameter optimization. So we've gone through these before. So we've got gas 1, gas 2, curtain gas and ion spray voltage. And these are things that we all need to consider when thinking about our source optimization. So once we've got those values, we can then look at our optimized LC method, and this just shows an example of the SciXOS software where we've chosen our optimized LC method. And then from step 1, where we've done our compound optimization, and we now know what our ideal declustering potential is, our ideal collision energy, and our ideal collision cell exit potential energy is, we can then input this into the method. When creating a method from scratch, it's good to first know and use generic source conditions. So this shows the source conditions, the curtain gas, gas 1, gas 2, temperature and ion spray voltage typically used for our different sources, with our Octaflow Pro ion source being specific to our SciX 7500 system. So important things to note when thinking about source optimization. So replicate injections are especially important for temperature optimization. And this is because, say, we have 3 injections for temperature optimization. It may take 1 or 2 injections for the temperature to actually reach the temperature we input. If you have a large panel of analytes, you'll need to make individual methods. Again, this just shows an example of source optimization. So for this specific compound, we can see there is an increase as ion spray voltage increases. So just to summarize, so method development does take time, so you need to plan ahead. And when building a method, you need to think about the 3 steps we've discussed today. And we need to start with your compound-specific parameters. Our LC method will also impact our source optimization parameters. And if we are adding components to a current method, you'll still need to follow the steps that are outlined here.